We're going to look at radioactivity in the kitchen, and in a way it could be radioactivity almost anywhere and in the past few millennia as well, because radioactivity is and has been everywhere, and it's called the background count. And I just want to familiarize yourself with materials that we come into contact with every day that have a certain radioactive component that has always been there, and half-lives excluded, will always be there. And so here are a few of the things that we will be looking at. Some building materials, a smoke alarm, water, some dinnerware, some food, and some other items as well. And to remind you that naturally occurring radioactive minerals in rocks, soil, has always been there. There can be very large variations in different places, as well as changes in a location over time. And the background radiation, always present on Earth, and is not harmful in normal life situations. Exceptions arise with accidents and perhaps with man-made applications. And here, a little bit about the background count. The blue glove in the right-hand photograph is holding the wand of a Geiger counter and can measure the background count, and indeed any other radioactive source as well. And you can pause to read the radiation units and the conversions, and you can also pause to read along the bottom where our average annual radiation dose comes from. And terrestrial is there, space is there, occupational is there, consumer, and you can read that more slowly. And indeed with this slide, which also looks at man-made on the circle on the left, on the left-hand side of that circle, and natural sources on the right-hand side. And for many people, about 48% of the background count actually comes from medical procedures. And then on the right-hand column, you can look at the different amounts in millirem at the bottom, 1 going up to 1,000 at the top. And another way of looking at the ionizing radiation, radioactivity that we experience each year in the US is actually giving values to this, inhaling food and water from the ground, from space, and then the medical consumer, and in previous history, atmospheric nuclear testing, etc. And you can pause this just to look at that. And the other thing we want to do with it is look at a periodic table of the elements. And the ones that are in yellow are the radioactive elements, but a lot of the others have radioactive isotopes, which may only be present in tiny amounts, but the vast majority of the elements there are going to have radioactive isotopes. And where does radioactivity come from? It comes from specific particles and rays. Here, an alpha particle from the disintegration of a radioactive unstable nucleus, given the Greek symbol alpha, and it's a helium nucleus. And the alpha particles don't penetrate the skin, but they do penetrate cuts and sores. It's dangerous if you inhale them, and it's dangerous if they're ingested. And beta particles small, fast-moving electrons, again emitted from breakdown of unstable nuclei, and they can penetrate the skin, but not too far, and they are dangerous when inhaled as well. And then we look at gamma rays, and they are the most penetrating of them all, in fact pass through the body, but they can damage DNA and cells on their way through, and shown there of the letter gamma with 0 mass and 0 charge. So in food, just looking at 2 items here, the isotope of potassium 40, but it's barely a 1/100% of any sample of potassium. So I certainly am not giving up my daily banana with breakfast, etc. And you can see the decay series going into 40 calcium and a beta particle. Carbohydrates, this is with carbon in, so proteins are going to have carbon in them, as indeed lipids, and they can decay carbon-14. The normal isotope is carbon-12, and this carbon-14 decays into nitrogen and a beta particle. And some more food materials here, and Brazil nuts, and you can pause to look at the nuclear equations that are here, and indeed more potassium 40 in carrots and potatoes. And in water, materials that contain radioactive isotopes that dissolve in water can be collected in your drinking water, but actually they're monitored. There are limits that should not be exceeded, and you can pause to look at the common radionuclides and where they come from, and indeed the limits that are there. And on the right-hand side, you've got a decay series, and here starting with uranium 238, and the half-lives are listed there, and the first uranium 238 loses an alpha particle to become thorium 234, and they've got different half-lives, and look at each of those to see which have the longer half-lives. And then in the air, a main contributor, and again very, very small amount in the open spaces, is radon, a colourless, invisible gas, naturally released from some rocks, particularly with fissures and cracks. And you can pause to look at the radon decay series, and indeed from how radon gets into your home. And it's thought that 1 in 15 homes have radon, but with the right ventilation, it doesn't become a problem. But it's worth checking your radon levels, and it tells you there how you can go through your state to do that. And then some people will have a glass that has radioactivity in it. It's known as Vaseline glass because of its sort of Vaseline-looking colour, and 2% of uranium was added in the manufacture to give it a sort of fluorescent yellow-green glow. And the uranium-238 is an alpha and beta particle emitter. And you can see some dose rates at distances from these samples of glass. Normal glass doesn't have any radioactive emissions. And then granite countertops. There's some uranium-238 in some granites, and you can pause to look at the decay series and the order of alpha and beta emissions. And you can also look at the disk in the bottom right-hand corner at the composition of granite, and it asks you to work out the nuclear makeup, how many protons and neutrons for each of the items in the decay series, and it gives you an example of how to calculate it for the first one. And then we go on to tiles, and you've got zircon in tile glazes, which have some emission, a thorium series, and it's known as a norm, a naturally occurring radioactive material that is used here for the surfaces of tiles in small amounts, and again, not that will add any significant amount to the count, the background count that you experience. And that's with uranium-238 and indeed with potassium-40 again. Now, way back, there was some radioactivity in crockery. The picture in the store in 2018, there is absolutely no radioactivity in the Fiesta ware, and it's popular, it's common, and it's fine. The pre-1972, two different colours had some radioactive glazes to them to get the colours that they have. That's only two of those colours. And if they're used normally, even those didn't pose a hazard if you were storing food on them for ages. Yes, there would be a problem. So the blue salt cellar on the left-hand picture, no radioactivity. The orangey one called radioactive red, pre-1972, and you can see the dial shoots round. And here are the colours, and the arrows at the bottom are pointing to the pre-1972 colours, old ivory and radioactive red. All the others and post-1973 onwards, absolutely nothing in their glazes. At the decay series, and what you actually have is the uranium-238. But two things. I've circled a lot of the isotopes because there's often more than one route that a decay series can go. And it ends in the bottom, not quite lowest right, with 206 Pb, a stable lead isotope. And this talks about the half-life of uranium, 4.5 times 10 to the 9 years, about the age of the Earth. And you can, the half-life is the amount of time for an isotope for half of the material to decay into its first decay product. 1 gram will decay to 0.5 gram in the same amount of time as 1 ton will decay to 0.5 ton. And so you're to research 5 of the isotopes on the decay series on the right-hand side. And then we've got smoke detectors. And the number of live smoke detectors save is enormous. There is no risk with the americium-241 in the smoke detector. Leave it there, don't tamper with it, don't harm it. And what happens here? The americium-241 emits alpha particles, number 1. Number 2, that energy ionizes neutral air molecules, N2, O2, other bits and pieces in air, and gives off ions and free electrons. The positive ions move towards the negative plate in the smoke detector. The electrons actually charge other neutral molecules, and those negative ions, anions, go towards the positive charge plate and complete the circuit. And in normal no fire situation, the circuit is complete. Any smoke in there, the diagram at the bottom on the right with the grey fuzzy bits, that blocks the current, and so the alarm sounds. You can pause that to read a little bit more. And the food in supermarkets, food in your cupboard, some of it has been irradiated. Why? It kills bacteria and molds that would make you sick. It slows down the aging of foods so they will spoil less quickly, and so no wastage and you can eat them. And irradiating dry foods, here we've got spices and grains, allows them to be stored for a longer period. So the activity, check in your food cupboard for that symbol, the logo at the bottom right, and check other products in the supermarket. Do the foods you discover surprise you? And why not? They're irradiated by gamma rays, but they do not make food radioactive. They don't affect the nutritional value of the food, just allow it to last longer. And so some building materials here, and in your kitchen, it's more likely to be plasterboard. You might have some bricks showing, stone showing, and we've talked about tiles and granite surfaces. But the cement blocks, cinder blocks, gypsum plasterboard, gypsum is calcium sulfate, and with radionuclides that we've met before, radium, thorium, potassium, uranium. And 3 of the nuclides have radon in their decay series. And why is radon particularly dangerous? Remember when we were talking about the air, that might give you a hint, as well as look at radon's position in the periodic table and what else is in its group. And then we're thanking Washington International School Team Science for their expertise.